the space of functions in G. And inside of this, we had the class functions in G. These are functions in G such that f of G H G inverse is equal to f of H for every H and G in the group. And inside of this, we had the subspace of the subspace H, which was spanned of the characters of irreducible representations. And we've shown that there's finitely many of them because, well, these are finite dimensional vector spaces. So in that set there, Vi is equal to the set of irreducible representations of G modulo isomorphisms. Isomorphism classes. Okay? And today what I want to prove is that that these two spaces are equal. But before doing so, let me just recall some corollaries of the things that we talked last time. So in the first case is that this as a representation of G, so O sub G is itself a representation of G. And what we proved by looking at the character of this guy is that the character of O sub G of the regular representation is equal to the sum of the dimension of Vi times the character of Vi. Number of irreducible representations. Right, so we proved, therefore, O sub G is equal to the direct sum of Vi, direct sum with itself, dimension of Vi. And this is the same thing as vector spaces. And this gives this side and representation of G structure is the direct sum of endomorphisms of Vi. So this side has an obvious G mod structure. G acts in each one of these VIs. And this gives this space a G mod structure that is not the usual one by conjugation in each VI, but just multiplication on the left. So every irreducible representation appears inside of the regular representation. So that's one thing. The second thing is we should notice the following. So what we get from this is we know what the character, we can see it from there, right? So what the character of OG, we computed it explicitly for each element G in the group is equal to the order of G if G is the identity, and 0 if G is not the identity. On the other hand, from this here, it follows that the character of OG, and this was actually the way we computed it, inner product with the character of Vi is equal to the dimension of Vi. And moreover, we have this statement that since we have this decomposition, we can evaluate both sides at an element G. So if we evaluate the character of OG at G, we have, well, on the one hand, this can be G or 0, just by that statement. On the other hand, this is equal to the sum of the dimension of Vi times the character of Vi evaluated at G. From where we get that a simple corollary that the sum of the dimension of Vi square is equal to the order of G, where the sum is over all irreducible representation. And we get the other corollary, that is that the sum of the dimension of Vi times the character of Vi of G is equal to 0 for every G different than the identity in G. So these are properties of characters of irreducible representations. And probably now I should switch back to Portunio. All right, so.
You can speak in English, I understand.
All right.
So fine.
I guess it's probably better than, it's not so horrible as my Portuñol, so I'm not sure about the video though. Anyway, so far no one has complained. All right, so this was more or less what we did last time, just pointing out this corollary, but this is a strong corollary. So we now know that we have finitely many irreducible representations of any finite group, and we also know that the sum of their dimensions squared is the order of G. I mean, of course, this came by knowing that to prove this, you just need to remember that the character of any representation evaluated at the identity is just the dimension of the representation. So you just plug in here G is equal to the identity, and you're going to get this expression here. So that's already an interesting statement. If you want to know what are all the irreducible representations of a group, and you've already found out a few of them that are irreducible and are not isomorphic, then this condition might tell you whether or not you found them all. The other corollary of what that we know from having a the notion that these characters were an orthonormal basis of this space H is the following, is that if W is any representation of G, finite dimensional of course, then W is written as a sum of Vi, direct sum to some Ni, I in the set of irreducible representations. And then the Ni's do not depend on the order, on the decomposition. Namely, you're not, if you decompose W as a sum of irreducible representations counted with multiplicities, then the only thing that might differ is the order in which you write the sum. But the irreducible components are just independent. And this is just the fact, this corollary follows from the stronger statement that the character of W identifies W. In other words, if the character of W is equal to the character of another representation W prime, this is if and only if W is isomorphic to W prime. And the way to know this is just, if both characters are equal, then you can write them, both of them, as the same sum in terms of irreducibles. Namely, the character of W is written uniquely as a sum of the character of W, the character of Vi, times the character of Vi. I is equal, well, I is in the irreducible representations. And this is the same thing for the character of W prime. So this is the multiplicity in which Vi appears inside of W prime. This is isomorphic to the sum of these numbers. Oh, these numbers is a bad idea. Vi raised to that number, direct sum of this, and this is the same thing as the direct sum of Vi to the character of W prime, character of Vi, and this is the same thing as W prime. So if you know the character of a representation, then you know what that representation is. So that's the strongest statement we've found so far, that traces, if you have a group acting by matrices in some place, then if you know only the traces of those matrices, you already know how the group acts. That's a very strong statement. And notice that historically it took a long time to understand these kind of things. Like, the notion of a group is an abstract notion. What we knew historically is symmetries of something. So we only understood symmetries, matrices, say, before the 19th century. The notion of a group actually just came, by definition, an abstract definition of a group structure only came in the 20th century. And somehow this is saying, well, you have this abstract object that is a group that acts as symmetry somewhere, and the only thing you need to know is what are the traces of these symmetries to understand how the action is. That's very surprising. All right. What else do I want to say about these generic statements we have so far? I think that's more or less it. Oh, perhaps just a criterion that we get for free too is that if we have two representations, so you decompose this W as a sum of Ni Vi with multiplicity Ni. I'm assuming that if Ni is equal to 0, for any vector space, I am writing this as the vector space 0. Then, if you have another one, W prime, to be as you decompose this, then the character of W, inner product with the character of W prime, since the characters of each one is the sum of these characters, this is just the sum of Ni, N prime J, the character of Vi, the character of Vj. And this is an orthonormal basis, so this is just the inner product of the vectors with integer numbers Ni and N prime I. In particular, that's an integer number, which this is a very strong statement. I mean, if you have a group, a finite group, acting on two spaces, or even in one space if you want, okay, you can take W to be equal to W prime, and just any action of any finite group by matrices on a space, and these matrices may be complex values, may be on any field essentially. Well, we used characteristic 0 and algebraically closed. Then this number is an integer number, and this number is well, it's a sum of traces of matrices, of squares of traces of matrices. So this is a very strong condition. Why in the hell, if you give me a bunch of matrices that are complex value, sum of traces of matrices have to be integers? And we got this for free, essentially. So again, this number here is the sum of these products, of the character of W, character of Vi, character of W prime, character of Vi, I in irreps, and this is a positive integer number. And moreover, this number, therefore, is a sum well, of non-negative integer numbers. And in particular, the character of W, inner product with the character of W, is a square, is a sum of squares. And it's equal to 1 if and only if W is irreducible. Right? Because if you have a sum of squares, then that number is 1 if and only if all of these numbers are 0 except one of them, and that one of them means that W is some Vi raised to the 1. Right? So it's only one copy of VI, so therefore it's irreducible. All right. Yeah, so I think that's as much as we can get just from the abstract construction last time. There was, and remember, so far we've only exploited one idea, that is, if you have a group action on a space, then the orbit of any vector is an invariant vector. That's the only thing we've used so far. We haven't had any other idea. We've exploited that idea to construct everything we constructed. For example, the fact that representations are unitary was the fact that we just took any inner product, then we took the orbit of that inner product, and that gave us an invariant inner product, which meant our representation was unitary. The fact that these characters of irreducible representations are orthonormal, again, was the same thing. Was just constructing any morphism between two representations, taking the orbit of this, that gave us a morphism of representations, and therefore it has to be 0 or a multiple of the identity by Schur's lemma. Actually, yeah, Schur's lemma perhaps can count as a different idea. Anyhow, let's move on to something new. So let phi be a class function in G. And let's take a representation it doesn't need to be reducible. Perhaps I'll use the name rho for the representation this time. Yeah. So notice the following, that if you look at the sum, perhaps I'll normalize it later, but I just want to look at this. I just look at the sum of rho of G, right? G in G. Perhaps let's normalize it. So I claim that this is an object that we've seen before. Let's call this guy, I don't know, I'll call this T. So what is this guy? So I claim that this is, in some sense, the orbit of an endomorphism of V under the action of G. Okay? So you can view endomorphisms of V as a G module. And you can view it in two ways. And we've already seen this in two ways as a endomorphism, as a module over the group G. One way was by conjugation. Namely, if you give me an endomorphism here, perhaps, that's a good name for an endomorphism, let's say P is an endomorphism here, then we can define an action of G on P by the conjugation. Rho of G, P, rho inverse of G. And this defines an action. So this makes this space into a G module. However, already in the regular representation of G, we've seen that given a representation of G in the endomorphism space of V, we can use a different structure of G module, which is just multiplication on the left. And that's also a G module. So we can grab P and send it to rho of G multiplied by P. You can check that this is a representation of G on endomorphism of V. Actually, viewed this way, what is this representation? This representation is just simply viewing the vector space K-linear endomorphisms of V as V tensor V dual, and then you view this vector space V dual as a trivial representation of G. So you take the identity representation in the vector space V dual that sends every G to the identity, and row on the vector space V and just take the tensor product of these two representations. So the tensor product of this representation row with the trivial representation of V star, that's the representation of an endomorphisms of V, where you just only act on the left. On the other hand, if you have a representation V, then I've shown how to construct another representation on the dual, which is not the trivial representation. Remember, how is V star a G module in a different way? And it's as follows. If you give me some sigma here, then G acting on sigma is equal to, and then evaluated in a vector V, we define that guy to be sigma of G inverse, of rho of G inverse, acting on V. So now if you take this representation of V star and you tensor it with V, with this representation, well, with V, with this representation, you get the representation by conjugation. That was one of the exercises in the homework. I think so. All right, so, but the point is, if I take this representation by multiplication on the left, and I look at one particular vector, the only vector that I have here, in endomorphisms of V, then this is the orbit of the identity. In endomorphism of V, I have only one marked vector, which is, well, I have two. I have the zero vector, and I have the identity of V. And this is the orbit of the identity by the action of G on the left. Therefore, this guy is an endomorphism of V, but it's invariant. And remember that the invariant endomorphisms are the same thing as the endomorphisms in the category of V modules, of G modules. However, we can try to generalize that a little bit. So suppose that now we are in the setting there where we have phi, which is a class function in G, and we have V, which is a G module, and we have some vector. Let me say W before, so that I don't confuse with that V. And we have some vector W in W. So then again, if I look at the sum of all the G's acting on W, and then I normalize this by G and G, this is a vector in W that is invariant. That's the only idea that we've exploited. But how about we look at phi of G, G of W? Is that vector invariant or not? So the question is this vector invariant? So this is something that not only depends on the vector W, but it also depends on the function that is a class function. So if I look at, I take another H and I act on this guy, then, well, this is a linear sum, so this is 1 over G times the sum. I'm summing over elements in the group. Phi of G, H acting on G acting on W, and H acting on G acting on W is the same thing as the action of HG in W. Now I wonder, how can I compare that vector here with this vector here? So one thing I can try to do is just relabel. Since I know that multiplication on the left is an automorphism, I can relabel this guy to be G. And then, well, then G is going to be H inverse times G. So this is the same thing as the sum of 1 over g of this function of h inverse times g, g acting on w. For g, g. And now if phi of g was equal to phi of h inverse times g, then I would be done. But that's not what having a class function would give me. Okay? So in principle, for a generic representation, then there's no reason for these two things to be the same. However, how about a construction like this one, where I'm acting on endomorphisms of a vector space? Okay. And let's try to repeat that construction there, where instead of acting on a generic representation, let's act on a place where I act by conjugation. So I now take W to be endomorphisms of V, and I'll construct, instead of that T there, I'll construct T to be 1 over G, the sum of phi of G times rho of G. Here, rho is the representation V. Okay? So this is a variation of the orbit of the identity on endomorphisms of V when I view it as a representation by multiplication on the left. But now let's look at endomorphisms of V as a representation by conjugation. So I'm using both of the structures at the same time. Okay? So therefore, I'm going to look at T now as an element in endomorphisms of V on this guy, but where the representation of G is by conjugation. So if I look by conjugation, then the same computation we just did there is what is H acting on T? Right? So this, by definition, is the endomorphism of V, which is the conjugation of H, T, H inverse, which is 1 over G, the sum of phi of G, and now here is rho of H, rho of G, rho of H inverse, which is this 1 over G, phi of G, rho of H, G, H inverse, and this is 1 over G, the sum over G and H, the same relabeling, G and G, I'm sorry, phi of H inverse G, H, rho of G. And since phi is a class function, then this is the same as T that we had before. Okay? All right, so the statement is that for any class function, so the corollary, for any phi, which is a class function in G, T as 1 over G, the sum of phi of G, rho of G, is an endomorphism of the representation V. So in particular, if V is irreducible, and the field K is algebraically closed, and we're using because of the normalization, but we didn't need the normalization. If I don't divide, this is still an invariant guy, and I don't need to divide. But then because of the normalization, I'll need that the characteristic that G inverse exists in the field. then if this happens and I have an endomorphism of a representation, then it's either 0 or a multiple of the identity, so it's a multiple of the identity. Then T is equal to lambda times the identity of V for some in the field. Okay, so let's use the same idea that we've used before, which is how do I find out what this lambda is? Well, just take the trace on both sides, right? So the trace on the right-hand side is lambda times the dimension of V. And on the left-hand side is the trace of this sum, which is a sum of traces. And the trace of rho of G on V, by definition, is the character. And now if you remember, this here was essentially the definition of the inner product between this function and this function, which is what we set out to prove, that there can't be a function here that is orthogonal to every irreducible representation. This is almost like what I had for the inner product. The inner product had a complex conjugate here. So if I take the complex conjugate of this expression, well, let's just not take the complex conjugate of this expression. Let me write this thing here as the inner product of phi with the complex conjugate of the character. And this is just lambda times the dimension of V. So that means that this T is equal to phi character of V over the dimension of V. And that's it, times the identity. And this is, on the other hand, that sum that I had there. Perhaps, so that we don't need to divide, let's put it here, and let's put here the sum of phi of G times rho of G. Okay, so we have that statement. Okay, so this we've proven for every phi, which is a class function, and any irreducible representation V of the group G. Okay, so now let's suppose that phi, inner product with chi of V, is equal to 0 for every V irreducible representation of G. Then in particular, then phi will be 0 with the complex conjugate for every V. So therefore, this thing here for any V will be 0. Okay? So what happens when V is not an irreducible representation? What can I say? So I'd like to exploit this thing when I'd like to construct something like this, but not using the fact that V is an irreducible representation. Let's get some time to absorb this term. Okay, so let's suppose that I take some V. So for any V, this statement was true. This was an invariant. Okay, and now I decompose that V, I decompose it in irreducible representations. Okay? then the statement is that this thing here, since it's, so let's do that before. So suppose you have a representation V, which is a direct sum of Vi to the Ni. Okay? Then suppose you have some T that is an endomorphism of V. So first of all, let's understand what is this vector space of linear endomorphisms of V. Okay? So this, as a vector space, clearly is the same thing as a direct sum over I and J of linear morphisms now from Vi to the Ni to Vj to the Nj. Right? So that's just any linear endomorphism between a direct sum of spaces. So now, for every I different than J, there are no morphisms between Vi and Vj that are different than 0. So we know that if I look at morphisms that are invariant with respect to the action of G, then the spaces are 0. So namely, if I look inside this space to the ones that commute with G, then this is the direct sum over I and J of hom G, Vi, Ni, Vj, and J. And now for I different than J, this space is 0. So this is the same thing as the sum over I of endomorphisms of Vi to the Ni. And this is the same thing as, well, now I'm in trouble, because between each one of these i's, right? So if I had Ni is equal to 1, this would be just a multiple of the identity, right? But what are the endomorphisms of this space? How can I write it in a better way? So just have what is the endomorphisms? And here I'm writing Ng. But what are the endomorphisms of a direct sum of spaces? Now what can I say? So my claim is, yeah?
I think it's like an operator by blocks, right? Where each block is a multiple of the identity.
That's correct.
Are different.
No, that's correct. That's how do I write that? How do I write in a clean way what an operator by blocks is?
Well, you can take I different than J.
Oh no, because I've already gotten rid of I different than J. Those were 0. So now I have just an endomorph. Oh, I see. So you want to write this as a sum again, as a sum of. That's not a clean. That's not what I call clean. Let's try something. Let's try a direct sum of endomorphisms of G of Vi. So this is at each summon, this is going to be an isomorphism. And let's just take any linear endomorphism of the field K to the Ni. And I wonder if this is an isomorphism or not. So I asked this for vector spaces. So let's suppose that V is a K vector space and N is a positive integer number. Is it true that the endomorphisms over K of V is isomorphic to the endomorphisms of V to the N? So this is what you call by blocks. To the endomorphisms of V tensor, the endomorphism of K to the N. This tensor product is over K. Okay, so how do we prove that then?
Maybe you can construct a map from right side to left.
Yeah, so it's very hard, I guess, to construct a map from here to here without choosing bases and orders, which is the viewing things as blocks. So if you view the matrices here as matrices by blocks, then you write this map this way. But this way seems to be a natural way of constructing such a map. Can you give me this map? That sounds like, again, writing by blocks. That I don't like. But okay, so I'll leave you as an exercise to play with this kind of thing. This is basically linear algebra, to check that this thing is an isomorphism. But the point of this isomorphism is that when V is a representation of G, this guy here is naturally a G module where G acts on each, well, forget about the Vn for a second. Right? V to the n is naturally a G module. G acts on each copy of V. Therefore, the endomorphisms is naturally a G module. On this side, the same thing. V itself is a representation of G. And this is the trivial representation of G, k times, n times. So endomorphisms of V is the same representation that I'm using here of endomorphism of V for G. And this is the tensor product of representations. So therefore, this isomorphism is an isomorphism not only of vector spaces, but it's an isomorphism of representations of G. Therefore, if I look at invariance here, which is by definition the G endomorphisms of V to the n, is going to be the invariance here. But every endomorphism here is an invariant. Right? So I get just the endomorphisms G of V tensor, that space which was just a multiplicity space. Which is what I wrote here. The endomorphisms here just tensor any matrix with constant coefficients. Okay? All right, so that's where I know if I started with my T on any representation, acting on any representation not necessarily reducible of G, then if I write this expression, then I know that my T lives in this space. Okay, so how do I exploit this? Remember, so what I want to do is, eventually I want to prove this. If I suppose that I have a class function that is orthonormal with every character of any reducible representation, is orthogonal to every reducible representation, then the class function is 0. That's what I want to prove. So what's the game that I can try and play?
Mm-hmm. Put row of G inverse there. Wouldn't we get the sum over phi j and chi j inverse? Wouldn't that be?
I think that's correct. Is it? So then you move away the conjugation onto the other side, which is fine. The trace is fine, and then you just get on the nose the inner product. That's fine. I think that's correct. Yeah, but that's, it's just a point. Okay, so the one thing I may want to try is to look at what is the picture in a representation that I know every reducible representation appears. Right? So I can try and look at V being the regular representation of G. Because I know that this guy here is a sum of, Vi to the Ni, and this Ni appears in a non-trivial way. Right? It's never 0. So I can look at that at T, which is going to be an endomorphism of that regular representation, which is invariant by the action of the group. I can look at my T given associated to that phi, which is now an endomorphism in invariant by G of that vector space. Right? In each, that's right, but this would be true, again, if I had a sum where each irreducible representation appears once. Now, each irreducible representation appears with a multiplicity, so for each irreducible representation, what I have is an endomorphism of this multiplicity space. But on the other hand, what I do know, so again, so I'd like to exploit this kind of structure. And what can I do? We have half an hour, and then after this, I just need to do examples, so we can just take our time. Yeah, so let's suppose that we want to analyze this when V is the regular representation.
Then you just multiply.
Then rho of G is just multiplication by G if we take this basis of e to the j, of e to the G, yes.
Just see the T U up.
That's a good, okay, so that's a good idea. So that's an idea that's going to leave us somewhere. So let's write it, right? So in here, we have a basis. And the basis, remember, was E sub G, where G is in G. In particular, I have one vector that is a marked vector in this basis. That is E of the identity. Let me write it E1, where 1, I'm using 1 in G for the identity. So this is a vector in V. And what we would try to analyze is what is T of E1. Right? That by definition is there 1 over G times the sum of phi of G, here G in G. And now I need to understand what is rho of G acting on E1. But the regular representation, remember, was multiplication on the left, right? So this is the same thing as E of G. Okay? Okay, good. So that's T of E1. So that's the one thing we can do. So now what else?
the lambda will be 0, so the t will be 0.
Wait. So now I'm a little bit slow. So why?
If you don't use that, in the definition you use
Yeah.
g inverse.
Okay, that's fine. That's fine too. Okay, I put G inverse here, and then
Then all the lambda will be 0.
why?
If you just look at each component of
Well, so that's the missing piece that I want. That is the missing piece that I'd like to hear an argument. So what I've proven is that if you have a class function, then and you take an irreducible representation V, then this T becomes a multiple of the identity in the irreducible representation. And that multiple of the identity, we've identified it with an inner product. But now, if you're looking at a representation that is not irreducible, then
I mean, if you look at the regular representation,
yeah,
it will be decomposed to,
yes.
then you can see.
But the thing is that the components are not irreducible, right? So I cannot. So one of the components is Vi to the Ni, which is not irreducible. This is Ni times Vi.
We cannot write it as vi.
We can. So let's write it as Vi plus Vi Ni times.
Then can we?
But the point is that our endomorphism does not need to be an endomorphism in each one of these copies. Right? So if you have an irreducible representation, there are, let's say that you take just V 2 times, right? What we know is that if I look at an endomorphism of V plus W and V and W are not isomorphic, then an endomorphism of this is the same thing. You write it as blocks, as you were thinking, and this is the same thing as an endomorphism of V here and an endomorphism of W, and it's just the sum of the two. But if you're looking at V plus V, and this is the whole point, then my endomorphism might have non-trivial off-diagonal components, because I can have a non-trivial endomorphism between this V and this other V. Right? So how, in each one of these guys, what I know is that this endomorphism is a multiple of the identity. Therefore, what I get is a matrix, which is 2 by 2, because I have only two components, with entries just what is the value of the diagonal element, which is just an element in the field. So in this situation, what I get is a matrix which is Ni by Ni with entries in the field, and that's this isomorphism.
But first we know the direct sum of Vi Ni times is not irreducible. It's reducible, right?
Yeah.
And so it can be write as the irreducible.
Yeah, so that's the decomposition in irreducible components. Here it is.
So we just assume it can write in irreducible, the direct sum of irreducible representations, and take the base of each of them. I think we can guard it.
I'm a little bit confused. So this is the composition of this representation as sums of irreducible. Each one of these components is irreducible. And now,
And it is the direct sum, right?
yes, correct.
So we take the base of each component.
Yes.
Then under that base, the matrix will be diagonal.
Well, that's the question. Why? To prove that this T is diagonal, I've used that V was irreducible. So now you're taking T that acts in a sum of irreducible elements. You can assume that all of them are isomorphic, but you have a sum. So all that I know is that T is an invariant matrix. I do not know that T is diagonal. Right? So any Ni by Ni matrix with which each block is diagonal would work to be an invariant guy. So, come on guys, you can do this.
blocks will have to be a multiple of the identity, right? Because if you just restrict T to like VI, direct sum of zeros.
That's correct. Yes, that is absolutely correct. So that's the whole point. That's why I only have nk to the ni. Yes. Each block is a multiple of the identity.
So now we have.
But notice what we're aiming for. What we're trying to prove is, this was in general. We just took our t in the regular representation, we acted on E1, and we've gotten this guy here. And the upshot of our proof is we want to check that this t here is 0. If this t here is 0, if this element is 0, then that proves that this phi is 0, because this is a basis on the vector space. Right? So what we're aiming for is to prove that t itself is 0. If phi is a class function that is orthogonal to every reducible representation. So what we're aiming to prove is that this t of E1 is 0. Mm-hmm.
Is the direct sum of that term, then we know that T is communicate with each rho G, right?
Yeah, so T lives here. That's all we know is that T is an element here.
I mean, if you have defined T as this, then T is communicate with each element in the morphisms of the rho G.
T commutes with the action of G.
Yeah.
Okay? Yes. So this means that T lives in this vector space. So being commuted with G, that's this sub G here. So it means that the component in this factor of the tensor product is a multiple of the identity. But this one might not be a multiple of the identity. Or at least you're not proving to me why that guy is.
We have that the OG is isomorphism to the direct sum of endomorphism in each VI, right?
Yes?
And according to the order of G is the sum of order square of Li.
Yes.
So we get the every endomorphisms of VI is the dimensional of each endomorphisms in VI should be Li squared.
Yes, that's true.
So, so the T is communicate with each. We can get T restrict to every.
It's not clear to me. So what I don't understand is why you cannot restrict T to VI. You can restrict T to VI to the NI. So you can only restrict to this guy. Well, you can restrict to one copy of this VI, but then the image might be in the sum. But we're in good shape. So I want to prove that T is 0, acting on that E1. So in particular, if I knew that the restriction of T, that if I knew that T was a multiple of the identity, and it was this thing here, so such that the restriction on each component, Vi to the Ni, was something like this, then I would be done, because this would imply that it's 0, this would imply that T is 0, and this would imply everything I want. So we are more or less in the right track. I want to prove that this T is 0, but the question is how? There's one little piece that is missing. So let's try to abstract this instead of like taking sums to the Ni. Let's try to abstract this thing. I mean, we've shown this for T being an endomorphism of an irreducible representation. Let's just take two irreducible representations that might be the same or not, and let's see what happens. I mean, that might help you getting the idea. So what happens if I just take I take two representations, V and W. Let's suppose that these are irreducible. And it may happen that V is equal to W or isomorphic to W. Let's just take this and let's look at that sum, right? So, and I define now T to be the sum of 1 over G, phi of G, rho of G, and now I have direct sum with tau of G, where rho is the map from G to GLV, and tau is the map from G to GLW. So the whole point was that it doesn't matter if I take G is equal to W or not. This endomorphism here, the way I defined it, is a direct sum. Namely, this thing here is 1 over G, phi of G, rho of G, direct sum. Right? So in one block, 1 over G, phi of G, tau of G. And now it doesn't matter if W is equal to V or not. Each one of these guys is an endomorphism. This thing here is in end G, V, and this thing here is a vector in end G, W. And this is inside of end G, V plus W. If V and W are different, so if V is not isomorphic to W, and they're both irreducible, then these two vector spaces are isomorphic. Then here I have an isomorphism. So if V and W are not isomorphic, then any endomorphism of V plus W that commutes with G is an endomorphism of V plus an endomorphism of W. But if V and W are isomorphic, then this space is strictly larger than this space. However, by construction, our T was already in this space. I constructed this as a sum. So then I don't need to worry about this K to the Ni, which are this component. That's why this space is strictly larger. Because in this space, I have those matrices with constant coefficients, which is the fact that here things would be matrices by blocks. But here I don't. This is just diagonal matrices block by block. So now it doesn't matter. In the regular representation, right, our T by construction is a diagonal endomorphism. So let's write it again. Let's write that corollary with this proof. Let's write it here. And this was now for any representation. So let's take phi is a class function in G. V is any G representation. Then you write T to be 1 over G times the direct sum of phi of G rho of G, G in G. Then not only T is invariant, if V is the direct sum of Vi to the Ni, and this is the decomposition of V in irreducible modules, then T belongs to the direct sum of endomorphisms of G Vi to the Ni. And again, the important step that we proved from here, with just that noticing that, is that this is not, in general, I would have gotten this sum inside. In there, I had this sum inside. Now I have endomorphism of Vi outside. That's the big difference. So I have a vector here for I in irreps, and in each irreducible component, and now I can restrict T to each one of these guys. In each Vi, T is equal to whatever that multiple of the identity is, which is G divided by the dimension of Vi times the inner product of phi with chi of Vi. So now I know that if my phi is a class function that is orthogonal to every irreducible representation, then T restricted to any irreducible component is 0. Therefore, T is 0. Okay? So if I have a class function that is orthogonal to any irreducible representation, then for any module V, then T restricted to any of its irreducible components is 0. This applies in the particular case where the regular representation is a representation where all irreducible components appear inside. And then we use that fact to prove that this T is 0. But then this implies that phi of G is 0 for every G in G. So this finishes the proof of a long theorem, which is the only theorem we've proved so far in this class, well, in the representation part, which is theorem. The characters of Vi, where I form a basis of the irreducible representations, form a basis, an orthonormal basis. Where are the erasers? Form an orthonormal basis. Orthonormal basis of the space of class functions in G, which in particular therefore is isomorphic to this H that I defined as a space spanned by those characters. So therefore we know exactly how many. As a corollary, we know that for a group there are exactly as many irreducible representations as conjugacy classes in the group. Corollary, there are exactly as many irreducible representations of G modulo isomorphisms as conjugacy classes. Of G. And moreover, we know more, so we know that if we take these VIs, so this is something I proved before, if the VIs are those, and now I can just say I is in conjugacy classes of G, because this is the set of irreducible representations now. Then what we know is that the sum of the dimension of VI, that's correct, square is equal to the order of G. Well, let's put it like this. Okay, this was just computing the characters, evaluated at 1. All right. Okay, so now we have enough tools to try to understand at least some groups. So let's start with the easiest ones. Okay? But any questions about today? Okay. Okay, so let's start with some groups. Let's look at. So what I'll do now is I'll write down character tables, because characters tell me everything about the irreducible representations. So a character table is like this. When you give me a group G, then what I'll do is I'll write a list of, here I'll just put the conjugacy classes in G, like C1, CK. These are going to be conjugacy classes. Here I'll put V1 up to Vk, which are the irreducible representations. And this number k is the same on both sides, because we just proved that there are as many irreducible representations as conjugacy classes. And here I'll write down the character in Vi of the conjugacy class Cj. So that's a matrix. Notice that this matrix is well defined because the character is a class function. So it depends only on the conjugacy class and not on the representative that I take. Okay? So that matrix there tells me everything I want to know, everything you can know about the representation theory of the group. And hopefully that's going to be enough to tell you everything that you know about the group itself. And again, notice that the representation theory of a group is much simpler to understand than the group itself. For example, people knew that the monster was a group that had an irreducible, a trivial representation of dimension 1, and then an irreducible representation of dimension, well, whatever it was, over 1,000. Okay? But they didn't know what the monster was. So it's easier to know what a representation is because you can compute what the characters of the traces of the representation would be easier than what the group is itself. Okay, so let's start with a simple group, which is S3. So for all symmetric groups, the conjugacy classes are parametrized for symmetric groups is by cycles. Every cycle of the same order, every 2 cycles of the same order are conjugate. Okay? So how many cycles of order 1 do I have? It's just the identity. And cycles of order 2, well, I have 1, 2, and then I have a cycle of order 3. So I have 3 irreducible representations of this group. So I have one irreducible representation that is the trivial representation, where everything goes to 1. So in that case, the representation of dimension 1, then I know exactly how the character is. And this I always have for a group. This one is always going to be an irreducible representation. Then the identity acts as 1. This guy acts as 1. This guy acts as 1. Okay? So now, let's try to find another representation. Any representation of dimension 1, that's an observation, any representation of dimension 1 is irreducible. So that's a good thing. So, and actually, we can say a little bit more. not the set, but now I'm going to look at a category. Representations of dimension 1 form a category. Morphisms are just morphisms of representation of dimension 1. So this is a subcategory of the category of representations. I no longer have sums in this category because a sum of two representations of dimension 1 is a dimension 2 representation. But I do have a tensor product. The tensor product of two one-dimensional vector spaces is a one-dimensional vector space. And I have a unit for that tensor product, which is the trivial representation. And the good thing about this is, I wonder, is a category like this, which has a tensor product, it has a unit, it's called a groupoid if a groupoid and a Picard groupoid if it's commutative that we have, namely if you have two representation of dimension 1 is isomorphic canonically to this, and for every L there exists another representation that I'll call L star, such that L tensor L star is the unit. So it's invertible. Notice the difference between having a group. This is an isomorphism, it doesn't need to be equal. However, it's true. For any representation, the dual is an inverse because this thing here is naturally isomorphic to the endomorphisms of L. And this thing here has a vector because an endomorphism space of a dimension 1 vector space, it has a basis which is the identity in L. I cannot say that these two things are equal because this is an isomorphism, it's not an equal vector space. Okay? However, these two are naturally isomorphic. Okay. Anyhow, so let's construct another representation of dimension 1 for the symmetric group of 3 elements. The symmetric group on 3 elements has a quotient that is the alternating group. Okay? So namely, this thing here and this thing here appear in the alternating group of 3 elements, which is just Z3, it's a cyclic group. And okay, so that gives me the sign representation of the symmetric group. So for the sign representation of the symmetric group, I'll write it like this. Sign is also of dimension 1. The identity acts as 1. This thing here is a permutation, so it acts as -1. And this thing here is a product of 2, so it acts again as 1. So that's the character of that representation. So I'm missing only one representation. Right? Because I know there has to be 3. And I know already what the dimension of this thing is, because 1 plus 1 plus whatever dimension of that new representation that I'm looking for should be the number of elements in S3, which is equal to 6. So therefore, I know that n has to be 2. So there's a 2-dimensional representation of the group S3 that is irreducible. And that's every irreducible representation is written in this list. And any representation of S3 is going to be sum of this. So okay, so it's missing another representation that I was going to write regular, but it's not, so I'll write it standard. And how I will produce this representation? I already gave you this representation before, so I'll give you as an exercise for symmetric groups.
What if you,
Yeah.
if you take a set of 3 elements, right?
Yeah.
You find the action of S3 on them by just permuting them.
Perfect.
And you quotient that space by the sum of them.
Good. So that's the exercise. Since we don't have time, I'm not going to write it. So the exercise is this. Take a set of n elements and look at the action of the symmetric group in n elements in that set. That gives you a representation of dimension n that is obviously not irreducible because the sum of all the elements in the basis is an invariant space. Then the quotient is irreducible. And that's called the standard representation of Sn. So that's true for every n. But let's check it actually in this case. So instead of looking at an irreducible representation, your name was? Luis. Luis's idea is to look at the defining representation of S3, which is looking at the action on a set with 3 elements. Okay? So what is the character of that representation? So, okay, the identity, remember, for any representation which is by an action, it's just how many elements you leave fixed. So the identity leaves fixed the 3 elements. Good. The dimension of that space is 3. This thing here leaves fixed 1 guy, 3 that doesn't touch. So there's a 1 here. And this thing here doesn't fix anything. So there's a 0 here. So now, this standard by definition is the quotient of this by the trivial representation. And remember, if you have a sequence like this, standard, the quotient is what defining. And the quotient is what I'm calling standard. Then the character of this is the character of this minus the character of this. So therefore, the character of this, I already know what it is without ever computing it. The character of this is 3 minus 1 is 2. Good. That's the dimension of this space. 1 minus 1 is 0. And 0 minus 1 is minus 1. And that's it. This is the character of any representation, well, of any reducible representation of S3. You can check. You can construct this representation explicitly if you wish. And that's it. So a nice exercise, I guess. I won't stop. I'll just take a couple of more minutes. I'll review this in the next lecture, checking, for example, that these 2 are perpendicular, that the norm of each one of these rows is 1. And then it's interesting to look at that in some sense the columns are also perpendicular. But that we're going to see later. It's something that I've already proven somehow. Okay, so let's do a couple more. Let's do S4 and A4. So S4 is a little bit more complicated because we have 1 here. So perhaps we're not going to finish. 1, 2, 1, 2, 3, and 1, 2, 3, 4. Right? So there are. Am I missing something? Come on. Good. So where do I put it? Right? So here I have some product of cycles, which I didn't have here. The product of 2 of these guys was this. So now, in which order should I put it? I guess I'll put it here. I'll put 1, 2, 3, and then 1, 2, 3, 4. I'm not sure. I don't remember what the standard is. 1, 2, 3, 4. Is that it? Okay. That looks like it. Okay? So okay, so we know that there are 5 irreducible representations. Let's do a couple of them quickly. We have the trivial one that is always irreducible. We have the sine one. Okay? Notice that tensor product doesn't give me anything new because the sine square is equal to 1. If you multiply this square to this guy, you just get this, the trivial one. The standard one, so for that, I'll just do again the same trick that Luis suggested, to take the defining representation, so that the defining representation for S4 has dimension 4. This thing leaves fixed 2 guys, 3 and 4. This thing leaves fixed 1 guy, 4. This thing doesn't fix anything. And this thing here doesn't fix anything. So the character of the standard representation is 3. It has dimension 3. 2 minus 1 is 1. 1 minus 1 is 0. 0 minus 1 is minus 1. And 0 minus 1 is minus 1. Okay. I'm missing 2 representations still. What else? So let's play with the sums, right? So this S4 has 4 factorial elements, which is 6 times 4, which is 24. And this is equal to 1 plus 1 plus 9 plus n squared plus m squared, which are the dimensions of the representation that I'm missing. So how can I do this? I mean, let's just take 11 out of 24, and we get that n squared plus m squared is equal to, how much is that? Is it 13? And now I need two squares that sum up to 13. Can you give me the answers to those? Sorry? Okay, so 9 plus 4 works, correct? And that's it, right? If I do 1 plus 12 doesn't work, and then that's it. So I know that the two representations that I'm missing is dimension 2 and dimension 3. Okay? So how do I do those? So the standard representation is dimension 3. I'm missing another of dimension 3 and one of dimension 2. So the beautiful, yeah? Sorry? Oh, that's a good one. If I tensor these two guys here, it's going to have to be irreducible. And okay, so I'll talk about this in the categorical sense later. But that's a good way, a tensor product. And here I'm going to get the product of these characters, right? So therefore, here I'm going to get 3, here I'm going to get 1, here I'm going to get 0, here I'm going to get -1, here I'm going to get +1, and I'm guaranteed that guy to be an irreducible representation. So now, my claim is that you get the character of this two-dimensional representation for free. If you know the rows of all of these things, right? So you have a basis for a vector space, an orthonormal basis for a vector space that is of dimension 5, and you already know 4 vectors, therefore you know what is the last remaining vector. So okay, so I don't want to take more of your time, but this follows from orthogonality. However, S4, so therefore S4 has an irreducible representation of dimension 2 that you can compute the character, and the question is how to construct it naturally. Right? So in the next class, I'll just do these kind of examples. And I'll just only do examples for 1 or 2 classes. Yeah.